All right, so I am trying to cover an enormous amount of material in about an hour here, and I apologize because I did what I know you absolutely shouldn't do, which is keep all the slides in there and hope you can whip through some of them fast. But since this is being recorded, I think that I maybe can do that, and you can kind of take some time on more of those slides as we move on. But I've broken it down into kind of 3 separate subtopics, and I'm going to start at the beginning with oil's physical and chemical properties, because if we're talking about oil spills, the first thing you need to do is understand what oil is. So what I'm trying to focus on here is what are the properties of oil and how do these properties affect behavior in the environment, and specifically response decisions and response options, since that's what we're interested in this case. So I'm not going to get into what makes an oil a good fuel or anything like that. We're talking about environmental behavior in this talk. So first, just what is oil, then what properties does it have, and then what's it made of, and how does that affect its behavior in the environment? So first, what is oil? We just kind of use the word oil out there, which actually has a lot of broad definitions. In this context, we're mostly talking about petroleum oil, which is a naturally occurring yellow to black liquids found in geological formations beneath the Earth's surface. So it's a natural product, which doesn't mean it's not toxic and nasty, but it is natural. What comes out of the ground is crude oils, and those are typically refined into various types of fuels and other chemical products, but it's the fuels we're worried about here mostly. And the important information is that each individual crude oil and each petroleum product that's made out of crude oil actually has a unique set of characteristics or properties. So if you just say crude oil or even fuel oil, you need to get a lot more specific because there's a lot of variation within each of those. For the most part, the sort of petroleum products derive from crude oil. And this happens because crude oil itself is made up of a very, very wide range of compounds. So literally thousands of different individual chemicals are in a typical crude oil. And some of these are very volatile, which means they evaporate easily. And some of them we call heavy compounds, which means they are very large molecules. And that means that they're less volatile and have different kind of physical properties. So the refining process in modern day refining is a great deal more complex than this, but at its core, it's not that different than it's been for 100 years or so, which is essentially you heat up the oil, and at each temperature you heat it to, different parts of it will boil off and you collect those. So when you heat up the oil a little bit, first you get gasoline, and then you heat it up some more and you'll get something like kerosene, and you heat it some more and you get something like diesel. It used to be it was as simple as that. That was the only thing they did. These days, there's all kinds of complex chemical processes going on to kind of more carefully refine and get specific products. But that's basically the gist of it. And that kind of helps us understand when we're working with these fuels, what we expect to find in them. So let's start with the bulk physical properties of oil. Sort of typically measured physical properties are density, viscosity, pour point, flash point, and interfacial or surface tension. So I'll run through the importance of each of those. So density is a very key question in oil spill response, because the question is this stuff going to float or not? And typically oils float. And that's because they're less dense than water most of the time. So density is described, technically density is mass per unit volume. So you have a certain volume of oil, how much does it weigh? How much mass does it have? And that's given in pounds per cubic feet, grams per cubic centimeters, all kinds of different ratios. Density is also often talked about in terms of specific gravity, which is the ratio of the density of oil to the density of fresh water. And that's kind of nice because that means if it's greater than 1, it's more dense than water. If it's less than 1, it's less dense than water. If it's less than 1, it will float. And then there's API gravity, which is this very peculiar unit used by the US Petroleum Institute, is defined as 141.5 divided by the specific gravity minus, I think that's 131.5. Since this is so common, it's a good unit to know about. One of the key things is you notice that you divided by the specific gravity. So that means that the higher the API is, the less dense it is. So high API means light, less dense, very much floating. And then some key things to remember here is freshwater has an API gravity of 10. So seawater has an API gravity of about 6. Seawater is more dense because it's got salt in it in addition to the water. So anything with an API below 6 is going to sink in all water. If it's between 6 and 10, it may sink in fresh water, float in salt water. If it's above 10, it will float. Most crude oils range in API from about 10 to 30, so crude oils are generally floaters. Gasoline has an API of 55 to 60. Remember, higher number, less dense. So gasoline's very low density, floats very well. And just keep it in mind, is we are certainly concerned about non-floating oils, but still most oils do float. And that's particularly true in salt water. So that's density is the number one factor. And now viscosity is another really important property. And viscosity is a measure of its resistance to flowing. Technically, it's the ratio of the magnitude of the shear stress when there's a velocity shear in the oil. But if you're not a fluid mechanics geek, it's just how easily does it flow? And we all experience this every day in the kitchen. You know, if you're pouring water, it flows out easily. And if you're trying to pour honey, it's really slowly oozing out. So that is viscosity that we're talking about. Key things about viscosity is that the viscosity decreases with increasing temperature. The warmer something is, the less viscous it is. That's something else we experience in the kitchen. The other thing is that as the oil weathers, and I'll be talking about that a little bit more later, but as the oil is exposed to the environment, it generally becomes more viscous and thicker. And why do we care? Well, this affects oil behavior in terms of how the oil spreads out on the water's surface, how it disperses into the water column, how it forms emulsions, and when it ends up on the shoreline, how easily it penetrates the shoreline. So if you think about that really goopy substance on the right in this image, and you imagine that on a gravel beach, it's just going to kind of sit on top. But if you have something thinner, the term is used as thinner, but less viscous, it will tend to ooze through into cracks and get deeper into the beach. So these are all why we want to understand the viscosity of oil. And it affects response options because different kinds of response equipment, skimmers, pumps, and whatnot are designed to work with certain viscosities of oil. So you want to understand what kind of oil you're dealing with, how viscous it is, because that's going to help you choose kind of what kind of response equipment is likely to work. The other thing to note about viscosity is that the viscosity has to change a lot in magnitude for you to kind of notice the difference. So as a kind of rule of thumb, an order of magnitude increase in the viscosity, this is in units of centipoise. Conveniently, a centipoise has the viscosity of water is 1. And really, it's not until you get to a viscosity of about 10 that it'll kind of be noticeably different. So diesel fuel is 10, olive oil is 100, honey is 10,000, molasses is 100,000. And oils in the environment that might get spilled really can be in this entire range. Gasoline is going to be like water, and obviously diesel fuel is diesel fuel. And then some of the heavier fuel oils will be right up there with molasses and peanut butter. So little example of, this is an interesting one about how density and viscosity together affect the spill response. So this is a really actually unusual oil. Maybe I should use a more typical one as an example, but this is the barge DVL 152, which had an incident November 11th, 2005. The barge impacted a oil rig that had been damaged in Hurricane Katrina, and the The part of the rig that was above water was destroyed, but there was still something just under the surface of the water, so they couldn't see it. And this barge hit it and ended up spilling a large fraction of its contents. So 2 million gallons were spilled, but very little was on the surface. In this photograph, you can certainly see some oil on the surface, but that's not 1 million gallons. And it turns out this is an oil known as a slurry oil, which is a manufactured product that's kind of the result of one of those complex refining products I talked about that I don't understand. And you end up with, end up with these very peculiar combinations of properties. It was very dense, had an API of 3.7. Recall that seawater has an API of 6. So an API less than 6 is going to sink in seawater. So this did sink. Usually oils that are that heavy are also very, very viscous. But in this case, this is actually a fairly low viscosity oil, around 15 centipoise. So that's only a little more viscous than diesel fuel. So this is quite, it flowed fairly easily, but sank. So it ended up on the bottom and looked kind of like that picture there. And the important sort of key things here are the fact that it was this dense meant that it sank. The fact that its viscosity was fairly low meant that it actually moved around down the bottom. It would form these sort of ropes. And it turned out in that depth, that depth of water was enough that the really, really large, long period waves resulting from storms actually were moving around the bottom and would mobilize this oil. So this is a very complex, hard to predict, and the response was really challenging because the oil was on the bottom and they sort of sent divers down with vacuums and tried to slurp it up. But very, very interesting that by knowing the density of viscosity oil, it told you a great deal about how it would behave and what you had to do to respond. Another key physical property related to viscosity is known as pour point. And this is defined as the lowest temperature below which a fluid cannot be poured. That's a definition, but it's not a very clear one. Sort of what does pouring or not pouring mean? It's kind of hard to know. So this is sort of a vague term. So you should always remember that the measurement of pour point can be fairly variable. But essentially, if you're below the pour point, then it's going to behave more like a solid than a liquid. And that's very helpful to know for response. So if an oil has a very high pour point, this means it might actually behave kind of like a solid, even in environmental conditions. So your kind of key response question is the pour point somewhere near ambient temperature? And really don't look at it in terms of within a degree or two, but if it's within 10 degrees of ambient temperature, you may be dealing with something more like a solid than a liquid. So I mentioned pour point is really not well defined. Oil does not freeze. It doesn't actually form crystals like water does. They have a very, very clear temperature at which that happens. It really is just gets thicker and thicker and more solid-like as it gets colder. And it depends on what lab technique you use to measure what you'll actually get. So this is, I think, a really fascinating thing. This is known as the, a little photograph here is known as the pitch drop experiment. This is at the University of Queensland, Australia. It is the world's longest continually running laboratory experiment. I think it's been running for something like 100 years. And essentially they put what they're calling pitch or bitumen or tar, they put it in a funnel and they let it sit there. And every 7 to 13 years, it forms another drop. So this is why we say this is certainly below the pour point. You kind of would think of it as behaving like a solid, but if you give it enough time, it will in fact flow. I just find that kind of a fascinating little point. So another really key property is the flash point. This is the temperature at which an oil vapor will ignite. So basically, if you are above the flash point, then you got a dangerous situation. If there's a spark nearby, you could end up with a really big boom. So flash point is totally about a safety issue. The lower the flash point, that is the colder at which an oil will burn, the more dangerous it is. So you want to be thinking in terms of is the flash point anywhere near kind of regular environmental conditions? Sort of rule of thumb is any flash point below 100 degrees Fahrenheit should be considered dangerous. So that's something to think about. This is a photograph of a gasoline pipeline leak in Whatcom Creek, Bellingham. So in the Northwest here, probably a number of you remember that one. It was a really, really tragic incident. But when you get a lot of gasoline in a little creek valley, you've got a very, very dangerous situation. A key note about flashpoint is that a lot of crude oils, especially lighter crude oils, will actually have pretty low flash points and can be quite dangerous when they're fresh, and then as they weather, they become less dangerous. So this is something to really keep in mind even immediately after a spill. For something like gasoline, we already know is dangerous for this reason, but it can be the case with crude oils as well. So in my usual way, I think I talked about all these things before I got to the slide. And so just as a note here, so gasoline is a flash point of minus 45 degrees Fahrenheit. It's basically always flammable, no matter how cold it is. Diesel fuel, not so much. And then here's a good example of Bakken crude. We've heard a lot about the Bakken crudes that are a result of the fracking process. They can have very, very low flash points and be quite dangerous. And we have heard about, there have been some train accidents with Bakken crudes that have been involved explosions and fires and whatnot. So keep an eye on flash point. Interfacial tension is the other sort of physical property. This one is not really talked about so much, and I'll explain why in a second. But we always heard that oil and water don't mix. So interfacial tension is the energy required to create new surface area. So basically, kind of stretching something out and making it bigger. There's this sort of tension that the oil wants to hold together relative to the water. So what this means is, since the smaller the droplets are, the more surface area there is. And so your surface interfacial tension tries to create large droplets and resist small droplets. So it takes energy to make small droplets. But when that energy is high, you will get droplets in water. So a key point here, and why we didn't used to talk about interfacial tension much, is because all petroleum products have a high interfacial tension with water. They all, quote, don't mix with water. They all form relatively large droplets. And this is why oil tends to form sheens on the water surface, is that if the oil sticks to itself, it doesn't mix with the water. But the reason why this is particularly sort of relevant for response is that one response technique we use these days is the application of chemical dispersants. And what a chemical dispersant is it's known as a surfactant, which means that it reduces the interfacial tension between the oil and the water. And now, with a much lower interfacial tension, than that oil and water still don't mix exactly, but it takes much less energy to form very small droplets with the interfacial tension reduced. So for the most part, the interfacial tension of one oil is similar to another's, but it can be affected by the presence of surfactants, such as chemical dispersants. And in fact, sometimes there are natural surfactants as well. So that's bulk physical properties. Now I'm going to kind of do a real quick run through on oil composition. Now we're getting a little bit out of my area of expertise. I'm not a chemist. I'm a physical scientist very much. So this is sort of the view of oil composition from a physical scientist point of view. The main thing is it's a mixture of many thousands of compounds. So oil is not one thing. It's primarily hydrogen and carbon. This is why they're called hydrocarbons. But there are other atoms, other elements there that can affect the nature of the oil itself. So organic chemists classify these into many classes based on their chemical structure. But that chemical structure also influences their properties and their behavior in the environment. So the ones we care about most are volatility, how easily does it evaporate? Solubility, how easily does it mix with water? toxicity, how harmful is it to organisms, and degradability, how quickly can microorganisms degrade and break down the material. And the amount of certain classes of compounds also can influence the bulk behavior of the oil, although for the most part, we just measure the bulk behavior of the oil. So this list in tiny little letters there, starting at pentane and hexane and going right up to methylisocyclohexane, are just a fraction of all the compounds in the oil. I don't think all of them are even named. But I'm going to leave the details for the chemists and the toxicologists, but it is good to be familiar with some of the commonly referred to groups. I'm going to whip through those really quickly because we're tight for time today, but I'm putting them in the presentation so you can review them more slowly if you like, looking at the recording. So first we have what are known as saturates. This is one of the most abundant hydrocarbons in oil. The thing to note about saturates is that they are relatively biodegradable. So that's a nice thing. And then we have aromatics. So aromatics include volatile organic compounds and PAHs, polycyclic aromatic hydrocarbons. This is another chunk, a good sized chunk of the oil. These are associated with toxicity. So usually we're concerned about the aromatics from a toxicity perspective. And the volatile organic compounds are the aromatics that evaporate relatively readily. And there's 4 of these that are sort of commonly treated as a group known as BTEX, benzene, toluene, ethylbenzene, and xylene. These are all associated with acute toxicity. There can be a few percent of this in a light crude, and gasoline is a very high percentage of these compounds. And then we have the larger, more complex aromatics known as PAHs. And this means they are not very soluble and they do not tend to evaporate. So these are because, and they also do not degrade very quickly. So these are associated with chronic toxicity. The PAHs are what people are worried about in terms of sort of long-term impact to the environment. So it's not a very large fraction of the oil, but it is the stuff that can do damage in the longer term. And then we have polar compounds, and these are kind of the bigger things that have some nitrogen or sulfur or oxygen in them. Often the 2 larger categories of these are asphaltenes and resins. And these are the ones that are responsible for the dense, high viscosity, heavy, goopy parts of the oil. So that was very fast run through. But so here are the key points to remember. If the flash point is below 100 degrees, it is flammable, it is dangerous, be very, very careful. If the density is above an API of 10, it will float. If it's below API of 10, it might sink. So that's our first kind of key points. And then viscosity. Remember that the viscosity goes down as it gets warmer, which means it gets up as it gets colder. And if it's more viscous, it will spread less, it will sink into shorelines less. If it's less viscous, it will spread more, sink into shorelines and things like that. As a rule, oils that are more dense are more viscous. So for the most part, those 2 go together, but not always. Remember that for pour point, if the water temperature is somewhere near the pour point, then the oil will not flow and it will be kind of chunks of gunk to clean up rather than a spread liquid oil. And then the chemical composition controls the physical properties, it controls how the oil weathers, it controls the toxicity of the oil. So those first few points are like your just first 10 minutes when you get a response, you want to know those basic things about the oil so you'll have an idea how to behave. And then we get in chemical composition in terms of longer term behavior, and especially impacts the environment, that starts to matter a lot more. My final plug here is for the Adios Oil database, which you can find at adios.orr.noaa.gov. And that is a NOAA maintained database of oil properties. And we've relatively recently revamped it. It's got a nice user interface. You can search for different types of oils and see a great deal about what kind of properties they have. So now moving on to oil weathering. So once oil gets released into the environment, it starts changing. It's exposed to the environment, exposed to the weather. And so it changes. And the key processes are evaporation, dispersion, dissolution, emulsification, biodegradation, photolysis or photooxidation, and oil sediment aggregate formation. So I'm going to kind of get into each of those and keep in mind the things we just learned about the properties of oil, because that has a lot of effect on how it weathers. I'm going to start with spreading, which is not technically a weathering process. It's a physical process, but it is really key to all the rest of everything else. So oil, when you spill it on the water, tends to spread out. This is initially driven mostly by gravity. It's essentially sort of flowing downhill if it starts as a big blob. This happens very quickly, and it just massively increases the area of the spill oil. So, you know, a 100-gallon spill actually covers a huge area on the water surface sometimes. How much it spreads and how quickly depends on the viscosity of the oil, how much oil there is, and the temperature, because the temperature really affects the viscosity. So the same oil will spread slower and less in, you know, the Arctic, where the water's 4 or 5 degrees C, than it will in the Gulf of Mexico, where the water is 30 C. The Northwest, somewhere in between. Once it's kind of spreads out, we kind of keep in mind that really within a few hours, there's winds, there's wave action, there's turbulence in the water. All of this will break the oil up. So that ultimately spreading is highly non-uniform. You'll have thick patches and thin patches, and it's just kind of all over the place. One thing that's sort of typical is that you end up with kind of elongated slick, where it's thicker at the front and kind of thin out behind it. This is sometimes called the comet effect, and this is caused by wind drift. So if you're out and there aren't a lot of strong sort of mesoscale, sub-mesoscale currents, and you'll downwind, this slick will form in this sort of downwind direction with the thicker oil at the front. Another thing is that the thickness controls the appearance of the oil to a great degree. So if it's very thin, it's going to give that sort of rainbow color that we see in this picture down here. To any of you who know him, this van belongs to Alan Mearns, biologist that's recently retired from our group. And he loved to take pictures of anything he saw when he saw it. So somebody had a little oil leak in their car, and that was probably just a drop or two of oil, but provides this large rainbow sheen. If it's very, very thin, it's a rainbow sheen. If it's a little bit thicker, it can be a silver sheen. And then as it gets thicker, it gets kind of more brown. An important part to note is once it gets thick enough to kind of look black, you can't tell the difference between 10 microns, which looks black, and a millimeter, which also looks black. So its appearance will tell you something about whether it's extremely thin or very thin, but once it's thick, you can't really tell the difference just by looking at it between thick and very thick. So this is kind of a quick overview of the processes we generally think about in oil weathering, scaled more or less by the sort of time scale in which they're important. So evaporation can be a very quick process, scale of hours. Dispersion, depending on the weather, happens very quickly. Dissolution a little longer, emulsification a little longer, sedimentation sometimes a little longer. Photooxidation and biodegradation are generally thought to be kind of much longer term processes, although they can actually kick in quite early in the process as well. And some of that we learned during Deepwater Horizon, that, at least under conditions in the Gulf of Mexico, that photooxidation and biodegradation are actually happening quite quickly. So evaporation is a big one. This is the transfer from a liquid to the vapor phase. We are very familiar with just general evaporation of, say, you know, water. If you have a puddle on the ground, it evaporates. It's a little more complicated with oil because, as I mentioned earlier, oil is made up of many, many different compounds. So some of those compounds evaporate fairly readily and some of them don't.
Say, Chris.
Yep.
You were broken up a little bit there. Maybe if you turn off your camera, We'll make sure that doesn't happen. Hopefully that'll give you some extra bandwidth.
Okay.
Thanks.
Let's see how that goes. All right, can you hear me all right now?
Sounds good.
Okay. So evaporation is kind of complicated with oil because it's a mixture of so many different compounds. But it can account for a substantial fraction of the oil and its loss. And so what happens as part of the oil evaporates is this will have an impact on how much oil is out there. It has a fairly small impact on density. Generally, the density increases because the volatile compounds are the less dense part of the oil. It can have a very significant impact on viscosity, actually, depending somewhat on the type of oil. And how quickly it happens is a function of environmental conditions. So the warmer it is, and that's usually the warmth of the water, because when the oil is floating in the water, it's going to be the same temperature as the water, and the wind speed. So the warmer it is, faster things evaporate. The windier it is, faster things evaporate. And of course, it is very largely a function of oil type. So evaporation kind of helps determine the time scale of the response. So this is an example of a kind of modeled oil budget where the conditions are the same. So 10 knot winds, 50 degrees Fahrenheit water, and 1,000 barrel instantaneous release. So if we look in the upper left here, we have a number 6 fuel oil, which is a very heavy oil, very, very few volatile compounds. So it will lose, a couple of percent and not really change much at all. And then we look at a Louisiana crude. And let's see, I need to hide this little window and then go back. A medium crude oil might lose up to 25% of it as volatile compounds. So over in the first 24 hours or so, you've lost 25% of the oil. You now have a more dense, somewhat more viscous product. And then you look at something like gasoline, and you can lose half of it in just a few minutes and virtually all of it just in an hour or two. So this totally determines the time scale of the response. So if you have a gasoline spill, it's a short-term problem, but that volatile nature of it also makes it very dangerous. And you're dealing with a heavy fuel oil, you're dealing with a long-term cleanup problem. That stuff is not changing much, and it's sticking around. Dispersion is not sort of technically a weathering process. It's kind of a transport process, but it's the other than evaporation, it's the other major removal of surface oil. So when you have turbulent energy, as I sort of mentioned earlier, with the interfacial tension between oil and water, it takes energy, quite a bit of sort of stirring energy to break oil into small droplets. But if you do have a lot of turbulent energy, and this is usually from white capping in the ocean surface, it can break the oil into these small droplets. And what this sort of distribution of droplet size is, it depends on the viscosity of the oil. It depends on the interfacial tension, which is always high for petroleums unless there's a chemical dispersant involved. And it depends on the environmental conditions, how much wave energy there is. So the more energy you have and the less viscous the oil is, the smaller the droplets it breaks into. And then what happens when these droplets are formed and stirred into the water column? Well, oil floats, right? So it starts to float back up to the surface. And here's a kind of a key point. Those of you that are math geeks, turns out if you've got a droplet here, there's a force of buoyancy that's trying to make it rise to the surface, and there's the drag force that slows it down. And the balance between those determines how quickly this droplet rises to the surface. Turns out the buoyancy force goes up with the cube of the radius of the droplet. So if you have twice the radius, you've got 8 times the buoyancy force. The drag force, on the other hand, only goes up with the square. It's the cross-sectional area of the droplet, so the square. So if you've got twice the radius, you have 4 times the drag force, but 8 times the buoyancy force. So what this means is that large droplets rise a lot faster than small droplets. If they rise fast, they make it back up to the surface. If they rise very, very slowly, then they're continually getting stirred back in with due to the background turbulence, and they'll never rise back to the surface and form a surface slick. So a rule of thumb, droplets smaller than about 50 to 70 microns won't resurface. So this is what we talk about when we talk about dispersed, oil being dispersed. And that can be just regular so-called natural dispersion, or it can be chemically enhanced dispersion. But either way, it's breaking the oil up into tiny little droplets that then rise so slowly in the water column that they just stay down there and stay mixed up and don't form surface slicks again. So the rule of thumb is the higher the wave energy and the lower the viscosity of the oil, the more gets removed from the surface by this dispersion process.
Yes, exactly.
So just a little example of this is the North Cape spill, which is in 1996, quite some time ago now. Couldn't remember if I had another slide on this. This was a spill of a home heating oil, which is essentially like a diesel fuel, under just massive storm conditions. So huge breaking waves. It was spilled near the coast. That picture is the tug that was towing the barge that spilled the oil. And essentially, all of that oil ended up getting mixed into the water column. So you didn't have a kind of surface slick that was an issue. But what you did do is you had a lot of impact on the biota on the bottom because it got mixed into the water column so readily. So you ended up with clams, lobsters, whatnot, were killed and washing up on the beach around there. So when you have a lot of dispersion, you don't have the same surface oil problem. The birds aren't going to have a real issue, but you've got some serious issues in the water column. Okay, so now dissolution. So dissolution is when the oil, rather than mixing into the water in very small droplets, the individual compounds actually dissolve and break down into their individual molecules. For the most part, oil and water don't mix. Most of the compounds in oil are not very soluble in water at all and will not dissolve, but some fractions will. It tends to be fairly closely related to dispersion because if you have a kind of big droplet or a slick on the surface, the soluble compounds can't make their way out of the droplet very easily. But very, very small droplets, the soluble compounds will make their way out into the water. So you can find these dissolved fractions of the oil just below surface slicks or in the water column around droplets. As a rule, the more volatile compounds are also more soluble, but not always. There are certainly compounds that are volatile but not soluble. But it means there's kind of a competition between evaporation and dissolution. So if you have a surface slick, a lot of stuff's going to evaporate and won't get dissolved into the water column. If you have a spill under the surface, then a lot of those more soluble compounds will get into the water before it reaches the surface. However, at the end of the day, it's a small fraction, somewhere between 0.1% to maybe 2% of the oil actually ends up in solution. And then once it gets into the water, it dissipates and dilutes fairly quickly. So it can be a substantial issue for damage assessment because it's the soluble compounds also tend to be more toxic. So that can have those kind of impacts on the biota. For response, not so much because there's nothing you can do about dissolved oil anyway. Just another little example in the deep water horizon. In this case, we had the spill down at 1,000+ meters. So there was a lot of opportunity for the soluble compounds to dissolve in the water before it got to the surface. This is a little transect here. And the the black line here is fluorescence. And oil compounds tend to fluoresce. So this is basically a measurement of sort of how much oil is in the water. And you see this big spike down there around 1,200 meters. And that is the components that dissolved as the oil was released and formed this kind of plume. So you had a lot of stuff that dissolved fairly quickly. A lot of that, by the way, is things like methane, propane, things that once they reach the surface would just evaporate into the air instantly. But will dissolve into the water column. And if you look also, the red line is dissolved oxygen, and you can see there's a little drop in dissolved oxygen right where that spike in dissolve in the CDOM is. And so what that's telling us is that that stuff is dissolving in the water column, and it is biodegrading, and the degradation is using up the oxygen. So you see that oxygen spike lined up. But again, dissolution is not usually a big response issue because you can't do anything about it anyway. Emulsification is a important process for surface response. So an emulsion or mousse is when oil and water get mixed up and you get little droplets of water mixed into the oil. And what this does is it creates what's essentially a very different kind of product physically. It's still oil and water. They haven't actually, they haven't dissolved in one another. They're the same thing, but it's, you got these little droplets in the oil. This requires turbulence. It requires oil with high wax and asphaltene content. So this is some of the kind of particular big compounds. Usually the oil needs to weather somewhat before it will form an emulsion. It also has to have a high enough kind of viscosity. So what's observed is that out there, day one of a spill of a crude oil, you won't see any emulsions forming. And then a couple days later, you start to see a lot more emulsion formed. This is partly due to the volatiles evaporating out and affecting the composition. And it looks, there's new research that seems to indicate that photooxidation may actually enhance emulsification. So it could be that once it's been out and exposed to the environment and to the sun, it can become more easy to form an emulsion. Generally, this makes it look different, changes the color. It massively increases the viscosity. It becomes very thick, heavy, almost sort of solid stuff. Think mayonnaise. Mayonnaise is actually an emulsion. So that's a similar kind of thing. It's totally different stuff than either the water or the oil by itself. And it can increase the volume quite a bit. So if you're going out there to clean it up and you're picking up emulsion, you suddenly have 3 or 4 times much stuff to store and deal with. So this is a very difficult to model process. Usually the best we can do is say that this oil is likely to emulsify or not very likely to emulsify. But otherwise, it's a matter of kind of observing what's going on out there and being prepared for it. Another process is known as sedimentation or oil sediment aggregate formation, sometimes also called oil mineral aggregate formation. It really depends on whether the sediments are minerals or of biological origin. Important note is very few crude oils, and in fact, not very many fuel oils are dense enough that they're going to sink in seawater. However, if sediment sticks to them, then they become more dense, and this is often the cause of the sinking. So this is an important process because it can make a real difference to where the oil ends up. This mostly occurs in the coastal zone and shallow waters where particulates are high and mixing rates are high. So you need to have a lot of sediment in the water, and you need to have something stirring and mixing them up so that the sediment particles come in contact with the oil and create these aggregates. So this very commonly happens at beaches. You'll get these oil mats kind of just underneath the water in the surf zone because of it all sticking to the sand. And it also can happen in rivers or near river mouths where there's when there's a lot of sediment in the water. A good example of this was the Westchester spill near New Orleans on the Mississippi River. And what we had were sheens going down the river, and they would just kind of disappear as they got before they got to the mouth of the river. And it was not an evaporation process, and it was not a dispersion process, but it turns out that it was sedimentation, the so-called muddy Mississippi. There's a lot of sediment in the water. It was sticking to the oil. And one way we know this is that the dredging operations that are always going down near the mouth of the Mississippi, they were picking up the dredge materials and they were depositing the dredge spoils in a marsh restoration project, which is usually a great idea. But in this case, all of a sudden after this event, those dredge spoils were starting to have sheen and oil in them. And so what was happening is the oil was floating down the river. It was getting stuck to little sediment particles in the water. And then it was settling out with the sediment that was then dredged. So this became a big because these were dredge spoils that were usually considered clean, and now all of a sudden they were contaminated. And there was a big hoopla about that. But so it can be a very important process in muddy rivers and especially near beaches. Another one, and this is kind of a new term that was coined after the Deepwater Horizon, known as MOSFA, marine oil snow sedimentation and flocculant accumulation. And it turns out that in the right environment, and the Gulf of Mexico is absolutely the right environment for this, that some of these sort of natural aggregates start to form. A lot of this is driven by biological processes. So you have algae in the environment and bacteria that are maybe starting to degrade the oil, and they form these sort of sticky mucuses things, and then you start getting all this stuff stuck together by the mucus, and it starts to sink out. And that these sort of particles sinking through the water column are known as marine snow, and this is marine snow is a natural process. In this case, though, there's marine snow with oil stuck to it, and then it accumulated on the bottom. So it's still not terribly well understood exactly when you won't get large quantities of MOSFA formation. You need the marine biota. It's possible that dispersants enhance this process. Certainly the salinity of the water, how much dissolved organic matter is, what sediments are, all those things are factors contributing. But at the end of the day, it's estimated up to about 14% of the oil release in Deepwater Horizon ultimately ended up sedimenting out at the bottom through this process. So it can be a fairly substantial transport process. Biodegradation is another big one. So a key point here is there are microorganisms that degrade oil in the ocean. These microorganisms have been found everywhere anyone has looked in the entire ocean. So certainly places where there's natural seeps, they are more abundant, but these microorganisms exist pretty much everywhere. So this is really the ultimate long-term fate of sort of all the oil that ends up in the environment. And there are natural seeps, so this has been something that's been going on for millennia, this process of oil getting in the water and ultimately being degraded. The problem is when we spill a whole lot all at once in one place, that degradation doesn't keep up. But it does go on. So different microbes degrade different parts of the oil. So it's not just like oil gets degraded, but all the different compounds get degraded separately at different places. And there are certainly some compounds that are much more resistant to degradation than others. So ultimately, degradation depends on, what bugs are kind of already in the water, how much oxygen is there, how many nutrients are there, what the temperature is, what the oil chemistry is, and droplet size. This is really important because if you've got a large droplet, the bacteria can only colonize the outer surface, and it can take a lot longer to degrade. So it is thought that, in fact, applying chemical dispersants help create much smaller droplets, and therefore it can degrade quicker. There are competing factors there, so it's not absolutely known, but it certainly can help. It can be quite fast for some compounds. So this was studied quite heavily during Deepwater Horizon, and there was a lot of degradation going on in a matter of days. But some of the other compounds will take, weeks, months, years. And it's a very difficult to model process. So still, we only really have kind of a gross idea of what's going on with degradation. And again, this isn't so much a response issue because, again, what degrades will degrade and what doesn't. And there's not a whole lot you can do about it. I want to mention tar balls. So over time, weathered oil, it becomes a little more viscous and it's getting stirred up, and eventually it gets kind of torn up into little chunks and smaller pieces. And at the end of the day, they form these little blobs of tar. And part of what happens is once it kind of forms a little blob, the outside of that blob will weather more and forms kind of a little bit of a shell. So there's fresh oil on the inside and there's more weathered oil on the outside. And those can be quite persistent. So it's very common that I will write up when I'm doing a trajectory analysis that the oil will form a field of scattered tar balls that are hard to see from the air. And I know this not because we have a model that can predict it, but because we've seen it happen over and over again. So the important bit of that is that once these tar balls have weathered a little bit, they stop sheening. So the outer surface, the more soluble, the more volatile, the more kind of lower viscosity stuff on the outside has gone away. And so you get these little blobs of tar floating. But since they're not sheening, what you have is a sort of 1 centimeter, ½ centimeter ball, you know, floating in the water from the ocean. You're not going to see that from an airplane. But so it'll look like the spill's all gone, and then a bunch of tar balls will show up on a beach downwind somewhere. So that's something we always want to keep an eye on. Photooxidation is a process of some of the compounds in crude oil when they are exposed to sun, mostly ultraviolet. They will oxidize and form different kinds of compounds. So this is kind of a new understanding. We've always known a photooxidation took place. We've always known, it's always thought that it was kind of a slow, long process. It turns out that sort of modern analytical chemistry techniques are able to actually, you know, measure these oxidized products in a way that they didn't used to be able to. And we've discovered that, in fact, quite a fraction of the oil is being photooxidized fairly quickly. So if you put oil out in a very, very bright sun environment, like the Gulf of Mexico, it is being oxidized fairly heavily. And now the question is, so what is the impact of this? Well, the oxidized compounds are sometimes act as surfactants, which will enable emulsion to form more easily. They tend to be more soluble, so there's potentially more compounds that wouldn't have been soluble are now becoming soluble and will get mixed into the water column and increase toxicity. And potentially dispersant is less effective on photooxidized oil. So this is still an ongoing area of research. We understand a great deal more about the photooxidation process and what's getting formed and how quickly, but the actual implications of that for response are still not very well understood, but something to keep an eye on. So in short, spill oil in the environment, it changes. It goes from being potentially flammable to non-flammable. It goes from being a liquid to being a solid or semi-solid. It becomes more viscous and potentially forms tar balls that are essentially solids. It goes from being smelly to not being able to be smelled anymore. And as a rule, it goes from toxic to less toxic. One note is that the toxic compounds are not necessarily going away. They just may be leaving the surface oil and getting into the water. So you still have the same toxicity issue. But the stuff that's actually floating on the water and flowing up to the beach tends to be less toxic after it's been weathered. So that's my high-speed run through on oil weathering. Let's pause for a minute for questions.
Thanks, Chris. And is that the complete end of your presentations?
No, now I want to talk about transport, which am I trying to do that? Do I have 15 minutes, 20 minutes, or do I have 4 minutes?
4 minutes.
Okay.
Linda did say that you could cut into her time a little bit. I'm not sure how much a little bit is, Linda, if she's on here.
Yeah.
Otherwise, I can ask her. But
yeah, how about 15 minutes, Chris? This is
Okay.
good stuff. So take what you need, and I'll go through mine fast.
Okay.
Awesome. Thank you, Linda.
All right, then I think I am going to jump right back in. All right, so going to talk quickly about transport processes. So the real question is, how does the oil get from out here where it was spilled on the water to sitting on the beach in tar balls? So we talked a little bit about very quickly the oil spreads on the water surface, and then it's weathering as it's going, and it's also being transported at the same time as all this is happening. So here's what I just went through with the weathering processes. These are all happening at the same time as transport. So let's talk about transport. After that initial spread, you know, in short, essentially the oil gets moved by the winds, it gets moved by currents, and it gets kind of spread out and stirred up and made patchy by turbulence. So these are like the three pieces we have to think about when we're trying to figure out where the oil is going to go. So you look at, where's the current going to move the oil? Where's the wind going to move the oil? Add those together, and that's where the oil is going to go. Simple vector addition. So let's talk about wind. So this is a little cartoon of what happens with wind blowing over the ocean surface. And what happens is somewhere up above the water, the wind is blowing free and clear. And then it's dragging on the water surface. And as it drags on the water surface, it brings a little bit of the water with it. So there's a little bit that, just a little bit of kind of velocity right at the surface of the water. Now, of course, it's a lot more complex than that in real life because of the waves and all the rest of that. But it turns out if you do this analysis, you end up with that the surface of the very surface of the water, and therefore the oil on the surface moves at about 3% of the wind speed, which is the square root of the ratio of the density of oil, water to air. So the analysis gives you that number, and it turns out in practice, actually fresh oil on the water does tend to move at about 3% of the wind. So that's what we use as a rule of thumb. So in a 20 knot wind, the oil's moving at about 0.6 knots, a little more than half a knot. So it gives you an idea of where the wind's going to push the oil. Other materials floating on the water will also get pushed by the wind, and that's something we do a lot in our work is look at other sort of floating materials. So this like styrofoam block floats very high. That'll move at like 10% of the wind speed. And this is actually an old boat that was floating around after the tsunami in Japan some years ago. And this is a bloated dead whale, which will also drift at maybe about 6% of the wind speed. This is a little example of how we can kind of use our basic understanding of wind transport to immediately answer response questions. And this is a little exercise we sometimes do. I'm going to whip through it really quick because we're short on time. But if we think about fishing boat sinks about 5 miles south of Dauphin Island, in this case, with 2,000 gallons of diesel fuel, and the wind's expected to be about 10 knots from the south all day. So the wind is going to be moving it towards the shore. And our question is, are we going to expect to have shoreline oil? So I'm going to just whip through. And this is, at the end of the day, a 10 mile per hour wind will go at about a third the nautical mile per hour. And that means it'll take about 17 hours to reach the shore. Okay. But this is a diesel fuel. And diesel fuel will evaporate quite readily. It gets dispersed into the water column quite regularly. And up here, we have model results that show that less than 10% of the oil will be on the water after about 12 hours. So what's happening here is this is where the weathering is the time scale of the problem. This is like a 12-hour problem, and it'll take 17 hours to get to the beach. So I'm going to, you know, when I write this up, I'm going to say we're not concerned about shoreline impacts. You probably won't get any noticeable shoreline impacts. The other note here is that this depends on wind speed. As the wind speed goes up, it moves the oil to the beach faster, but it also disperses it faster. And these are nonlinear. So in summary, we did the 10 knot wind. If you had only a 5 knot wind, it would take a lot longer for the oil to get to the shore, but also it's not getting dispersed into the water column at 5 knots. And so you may still actually get some diesel fuel hitting the shore a couple, you know, a little more than a day later in a very light wind. And then in a 15 knot wind, it's moving towards shore a lot faster, but it gets dispersed massively faster. So in strong winds, diesel spills go away quite quickly. All right, that was the quick run through wind. So now currents. So currents are very straightforward. And basically the oil is floating on the water and the water's moving, the oil's gonna move with the water. So that part is easy. There's no 3% rule. There's no nonlinearity. However, you have to actually understand what currents are doing. And depending on where you are, the currents can be very different. So this is going to be a quickie on Physical Oceanography 101. Currents are driven by gravity. They're driven by the Coriolis effect. They're driven by density differences, and they're driven by wind. And ocean currents can be very short-term in some places or long-lasting. And they can be near the ocean or deep ocean. So this visualization is just very, very cool, showing the really complex circulation that goes on at the oceanic scale. So let's start with rivers. I believe I had a question earlier about that. So I like to say rivers are easy. People have a spill in a river and they say, where's the oil going to go? It's going to go downstream. There you go, done. So rivers are pretty straightforward in that regard. However, the actual velocity of the flow can depend on the water volume, the steepness of the gradient, the topography of the river. And this can get a little bit complicated because our rivers in the US are pretty well gauged, but what they'll tell you is how many cubic feet per second is flowing down the river, which is not necessarily tell you how fast it's going. And sometimes that's a kind of a tricky thing to compute. When the river starts getting close to the ocean, you have tidal influences, then it gets a lot more complicated. You can have it flowing upstream or downstream, or you could have the tide rising, but the river still flowing downstream. It can get kind of complicated. They can be quite dynamic. So if there's a storm, you could have the river conditions can change a great deal from one day to the next. So we have to keep track of that. And then there's the whole question of shoreline stranding. So the oil will move downstream, but it also will get stuck on the shore. And if it gets stuck on the shore, it's not moving downstream. For the most part, you think about the oil is going to get moved downstream by the river currents, and then the wind is going to tell you which shorelines are more likely to be affected. So if the wind will push the oil from one side of the river or to the other and cause it to strand in the shoreline. And sometimes you can get oil caught up if the wind is blowing towards a river bend. You can get oil kind of caught up in that river bend, and it'll get naturally collected there. But then when the wind lets up, all of a sudden it's flowing downstream. All right, tidal currents. My graduate advisor said that the tides are the geophysical prediction success story. It is the only geophysical phenomena that we can predict with incredible accuracy, months, even years in advance. So that's really pretty darn cool. The tides are driven by the gravitational effects of the moon, primarily the moon and the sun, but also other wobble of the earth and other astronomical properties. But the moon and the sun are the big one. And because those are moving in predictable ways, it means the tides move in predictable ways. It turns out it's very difficult to actually compute from first principles what the tides will be in any given place. But if you can go and measure it for a little while, you measure it for about a month, you can then predict it years in advance. So we have tide stations just all over the place. I think Faith had a little map of that for the Northwest. So the tides are very well predicted and understood. Tidal currents are equally predictable, but much less, many fewer stations, because you actually have to put a current meter in the water, keep it out there for a month, and that's much more difficult to do than just a tide height. But nevertheless, we have most major ports. We've got tidal current stations. We know what the tides are doing. For the most part, it's about a 12-hour and 24-hour periods. So if it's primarily 24-hour, it's called diurnal or daily tide. Semi-diurnal is twice a tide. The Northwest, we mostly have semi-diurnal tides. The key point about tidal currents is that tidal currents can be quite strong and quite fast, but they will ebb and go out towards the ocean really fast, and then they slow down and stop and slack and turn around and come back the other way. So on short time scales, we can get very fast tidal currents, and it can move oil a good long way, just a couple of hours. But it's going to move it back the other way. So on the longer time scale of more than a day, the tides tend to be moving the oil back and forth and not moving them a long way away. So that amount that one tidal cycle will move the currents is known as the tidal excursion. And tidal excursion is, you can, and the rule of thumb for tidal excursion is about 4 times the peak velocity. So if you have a 1 knot flood tide, you can get about 4 nautical miles of tidal excursion. So how far the oil will move before it turns around and comes back the other way. So tidal currents are very predictable, can be quite fast, but not a long-term transport mechanism because they're oscillatory, go back and forth. Estuary circulation can be very complicated. The actual circulation within an estuary it can be driven by the tides. That part is fairly predictable. River flow can then change the circulation quite substantially. You've got this mixture of fresh water and salt water, and sometimes you get a freshwater lens of the fresh water floating over the salt water, and the currents can be moving in opposite directions in those 2 parts. So, and then you combine that with the whole ecosystem, and the resources within estuaries are very important and very complicated. So estuaries are the big challenge. The major estuaries these days, we have good models for, like the Columbia River estuary, and which can be quite helpful. But often this is the tough one for kind of the detailed transport. Coastal and shelf currents. So these can be pretty complicated dynamics. It can be driven by the wind, freshwater influence, by major river inflows. Also what's going on out in the deep ocean. We saw in that animation earlier that you can get these big eddies that kind of will impinge upon the coast. And there's tidal flow. And of course, it's interacting with the topography or bathymetry of the undersea surface. So coastal flows can be kind of tricky to predict. There's a lot of variability from day to day, both seasonally and on shorter timescales. So hard to kind of get a grip on that. Again, we're getting to have better and better models. NOAA recently has implemented the West Coast ocean forecast system, which is a sort of shelf near coast scale model for the whole West Coast, which is helping. But can be tricky stuff, but something we need to keep an eye on. And coastal currents can kind of go in the same direction for quite some time. So they can be a substantial transport mechanism over days or weeks. Then there's basin scale currents. So these are the big ones that sort of explain the circulation throughout the global ocean. And so these are things like the Gulf Stream in the Atlantic Ocean, the California current, the North Pacific current. So these are usually kind of these large scale circulations that are really not particularly relevant to oil spill timescales. Your oil has weathered and formed tar balls and scattered within a few days. But they do affect kind of ultimately where stuff ends up for more persistent pollutants and in the long term. A good example of that was at the tsunami in Japan in, I think, 2012. In there somewhere, there was an enormous amount of debris was washed into the ocean, and this debris circulated around the Pacific Ocean for literally years, and ended up on our coasts and all over the place. So this was all caused by these kind of large-scale circulations. So quickly, going from rivers, which have the lowest uncertainty, but they can be substantial go tens of miles very quickly, hours to days. Tidals have length scale of miles, time scales of hours, low uncertainty because they're quite predictable and consistent. Estuary and circulation can go tens of miles, time scale of days, and there's a medium uncertainty there because of these complications with salinity and river flows and all that. Coastal flow can go for hundreds of miles over timescales of days to weeks, and there's a really quite a high uncertainty on the coastal flows. It's hard to predict those. And again, ocean scale circulation can literally go thousands of miles in months to years. And at the large scale, the uncertainty is low. The Gulf Stream is always going off to, Northern Europe, North Atlantic, but can be quite high uncertainty at the smaller timescales because they form these eddies that are very dynamic and move around a lot. So our resultant movement is current and wind. We know where the oil is going to go if we know those two things. However, This is what we actually see on the water surface. And so this we kind of lump into the category of turbulence. So this is the smaller scale fluctuations of currents and winds. If you think about, say, leaves getting blown around in the wind, if the wind may be forecast and be about 10 knots from the north, but the leaves don't all pick up and move as a group downwind. They get scattered and blown all over the place. And the same thing happens with oil on the water surface. So turbulence ends up really doing two things. One is it spreads out the oil, makes it cover a wider area, and it breaks it up into patchiness. So you get high dark patches of oil and clear water in between, and just all kinds of complications. And this has real implications for response because it's getting spread out like that. It's very hard to know, like, how thick is the oil going to be, exactly where are we going to be able to use skimmers and that kind of thing. Another thing that happens in the ocean, these sort of opposite of diffusion, are convergences. There's certain circulations that actually bring surface water together. Some of these are Langmuir circulation, which forms wind rows, these lined up lines of oil. When you have fresh and salt water coming together, you can get a very sharp line between them because the fresh water is kind of floating above the salt water. That's what this picture in the lower left is. The brownish water is actually fresh water coming from a river, probably the Mississippi River, with a fair bit of mud on board so you can see it. And there's this very, very sharp line. And this has implications for response because these are convergences tend to bring the oil back together. So it's spread out and it's all scattered, and then all of a sudden it comes together and becomes thicker. And on the one hand, that's good because you can go and drive a skimmer down that thick oil and clean it up. But on the other hand, the same physics that's bringing the oil together also tends to bring together whatever else is floating on the surface, which can be sargassum, which is a vital environment that can be floating rafting birds, turtles, whatnot. So unfortunately, these convergences tend to collect the oil and sometimes sensitive biota in the same place, which is an unfortunate outcome. So when we have people out there on overflights looking for oil, we also have them look for these sort of convergences so we can have an idea of what's going on there and where we should expect oil to collect.
Hey, Chris.
We're running out of time, aren't we?
Yep.
Okay.
How much?
Let's see. So oil ends up when it gets on the beach. If you have wind blowing towards the beach, it's more likely to stick to the beach. There we go. Final thought.
Perfect.
So the key point is the oil properties make a big difference in the first few hours, the first day or two. And after that, we're really worried about transport. And that's mostly driven by the atmospheric and oceanographic position, conditions. Remember that as the spill progresses, it's going to get patchy and distributed over a wide area. That's just one of those things to always keep in mind. And even though it's getting spread out like that, also it can sometimes get recoalesced in surface convergences. So that's something to keep an eye on. So there we go. I do have a couple slides on non-floating oils if we want to talk about those, or we could talk about those later, or whatever you want to do.
Linda, what do you want them to go into those now really quick or later?
Yeah, I mean, let's make sure we get that in, please, because there was a question about that and it is emerging. Thank you, Chris.
Okay. Sorry, there's just so much to cover here. All right. So non-floating oils, or NFOs. So if the oil has a density greater than the water, it's not going to float. There, simple as that. However, this brings a lot of complications. So if it doesn't float, it's going to sink to the bottom, but that doesn't mean it's going to stay there. It can still be transported. But the transport of oil is on the bottom is much less well understood than it is on the surface. As I said, on the surface, it just, it moves with the currents. And then it gets pushed a little bit by the wind. There you go, we're done. But oil on the bottom is it may be stuck to the bottom. It may be in little hollows and things. And then what is the velocity on the bottom? Is it going to move like sediment? And sediment transport on the bottoms of rivers is also very difficult to model. So all these are really complicated. It's going to depend on the density of the oil, the viscosity of the oil, the sort of topography of the bottom, what's going on with the currents. Also, if you're in the coastal zone, if you're in shallow enough water, the waves can then be stirring things up. So all of that are complications. And so we have a very high time kind of modeling transport of oil on the bottom. Also, it's a whole lot harder to see and track. So one reason we do as well as we do with forecasting surface oil movement is because we can see it. So we know where it is, and then someone flies out tomorrow and says, oh, it went from this place to that place in the last day, and we can recalibrate our models and get a better forecast the next day. When it's on the bottom, it's much, much harder to see. There's this whole process for trying to track where the oil's going. And so that really, really complicates things. So what kinds of oils are we worried about? So there's one way of categorizing oils known as the groups, group 1 through 5. And group 5 is basically defined as heavier or more dense than water. So group 5 oils sink. So the ones we tend to encounter are asphalt and bitumen. Bitumen and asphalt are very similar, except bitumen is a crude product. It's as it gets dug out of the ground, but it's very much like asphalt. Asphalt is a refined product. These are very dense, they're nearly solid, and they often are denser than water and will sink. We actually had a asphalt barge incident on a river back east. I'm trying to remember exactly where, but the asphalt was actually heated in the barge so that they could pump it on and off the barge. And then the barge ran up on a bridge pier and tipped over, and the asphalt was like oozing out of the barge because it was still hot and liquid. And it would float down the river, and as it cooled, it actually became more dense. So it floated down the river as a liquid, and then it kind of solidified and sank as it moved downriver. So a real mess there. Another potential sinker is dilbit or sinbit. And these are a mixture of bitumen, which is this very heavy asphalt-like stuff, and some kind of diluent that makes it flow. So when this is fresh, as it comes out of the pipeline, it is less dense than water, but it's a mixture of this really heavy stuff and this diluent, which is quite volatile. So once it weathers, the question is it going to sink? So here's an example. Cold Lake Blend is a Canadian dilbit. And when it's fresh, it has a density of 0.923 grams per cubic centimeter. So that is definitely a floater, quite a bit less dense than water. However, when it's been weathered, and this is according to weathering it in the Environment Canada lab, it becomes just over 1 gram per cubic centimeter. So that would then mean it would be a sinker in fresh water, still probably float. So in seawater. So here you have these oils that might well float when they're fresh and not when they're not fresh. And the other one we've had for sinker is slurry oil. And this one I mentioned with the DBL 152 incident earlier. And then we had another one, the tank barge Apex on the Mississippi River. And both of these were very dense oils that sank right away. The DBL 52 is relatively low viscosity, so it ended up getting transported and dispersed on the bottom. The Apex was actually much more viscous. So sorry for the typo there. So it sank to the bottom and kind of settled into some low spots on the river and just kind of stayed there. So they were basically able to clean most of that up by just actually using like a clamshell kind of dredge type device to dig it out. So these are complicated problems, and we're still working on some of that. I think someone asked a question about this, and this whole question of how oil moves on the bottom it's ongoing research. There was some work done at University of New Hampshire in the last couple of years where they were looking at a model for how these heavy oils might move on the bottom, coming up with the criteria based on the thickness of the oil, the viscosity of the oil, and the flow conditions. So we're getting there, but probably the best we'll get to is sort of it's likely to be moved under these conditions or not. And ultimately, that big question of something that starts floating, will it end up sinking? And it's always the big question. Okay, that's what I've got.